let's take a look at the derivative sensitivity under the Black-Scholes formula. So if you look at the price of a derivative product and the change of that price by, let's say you take the Taylor's expansion, then you get a bunch of first partials, and you can drop off the higher order terms, but here it turns out that the second partial for the price is actually important as well. So you can basically approximate this with this expression here. And in finance, they all have, because they're important enough, they all have their own names. So this part, the partial derivative of the price of the derivatives asset related to the underlying asset is called delta. Okay, it's a bit of a misfortune that don't get confused with this delta with that delta. This delta here means the sensitivity is the partial derivative. This delta here means the change. Okay, so we call this change of f is delta times the change of s. Okay, so don't get confused here. It's just notation stuff, which is unfortunate. So the first derivative, first partial, is called delta, and which gives you the linear change. And the second partial here gives you the curvature. So this one has a Greek name called gamma. Okay, and then we have this part related to the volatility. We call them vega. So this partial derivative here is called vega. And this partial derivative here is called theta. And the partial derivative related to interest rate, we call that rho. Okay, so they all have a Greek name. And so typically in the industry, we just go by delta, gamma, theta, vega, rho. So you have to know what they actually means. So now within the Black-Scholes Merton framework, because they assume that interest rate and volatility are constant, in that formulation, the meaningful sensitivities are only three. The delta here was the first partial related to the underlying asset, the linear change, and the curvature of that, and also the change related to the passage of time. Now, this change is actually deterministic because it's related to time itself. Now, although in the Black-Scholes Merton framework that volatility and interest rate are constant, but in reality, they are actually, you can see them, they are stochastic in nature. So people do calculate sensitivities for volatility and sensitivities related to interest rate. So vega and rho are actually also used in the actual sensitivity analysis in the industry. Well, the if we are taking the Black-Scholes formula and you take the partial derivatives, you will actually derive the actual form for delta, gamma, vega, theta, and rho. They will be given in this table here for a derivative based on an underlying asset that pays no dividend. If the underlying stock pays dividend, the actual form here will be a little different, and we're gonna show that later on. Now, in this course, you are actually expected to be able to derive those ones if you are given the Black-Scholes formula. In a lot of the lower level courses, you probably just be given this, but it's good to have that skill to be able to derive those things, such that in certain situations that you need to do, certain derivation, you actually experienced and practiced. So in order to derive some of those conditions or some of those the forms here, then you need a few conditions and identities that may be helpful for you. So one of the things that's commonly used is this equality here. So basically, S times m prime d1 is equal to m prime d2 times k times the e to the power minus rt. Now, let's see why that is the case, because this is typically used in situations to allow you to derive them in this particular form. Now, m prime x basically is the derivative of this cumulative distribution, which is really the normal probability density function here. And if you have that, then okay, m prime d2 was m prime d2. So x here you substitute with d2. So d2 is d1 minus sigma square root of t. Okay, so you do a substitution here. And once you have done that, you can break them into different components. So this square here, you can just have it multiply through. You have d1 squared minus 2d1 times sigma square root of t and plus sigma squared t here. Now, once you have done that, you can, so you have this 1 over square root of 2 pi e, and just put this out, minus d1 square divided by 2, okay? Then this two parts here is what? Well, you have this red one, you just pull it out like e to the power of minus, because the minus sign here, sigma squared t divided by 2. Now you're left with this middle part. So the negative sign here, the negative sign here is positive. So you have a 2 here, 2 divided by 2 is basically 1. So what is d1 sigma times square root of t? So d1 sigma times square root of t is basically, this is d1, this sigma times square root of t. So in d1, there's divided by sigma times square root of t. So these two parts canceled out. And then you're left with the numerator here. And so you can substitute this part when you have the d1 sigma square root of t. So that will give you e to the power of log s divided by k plus rt plus sigma squared divided by 2 times t. And then you have two, this is a minus, this is plus, so this two canceled out. And then you just have e to the power log long s divided by k, which then is just s divided by k. Okay, so all this part becomes s divided by k. And if you look at here, this part is really just m prime d1. Okay, so you have m prime t1, m prime d1 times e to the power of rt times s divided by k. Okay, so this part here is from this e, this rt here. So then you multiply through, you will get k times m prime d2, and times, you have this move to this side, will be e to the power of minus rt is equal to s times m prime d1. So that you derive this particular condition here. Now, this condition is useful. We'll see that later on in our actual derivation of the delta, gamma, vega, theta, and rho. There's a different way to derive the same condition. I'm not going to belabor on this particular one. It's an equivalent way of deriving that.